So let's talk about how that gradient is actually established. So it's established by the counter current multiplier. And the counter current multiplier is just a fancy name for the movement of solutes across the ascending limb at first, and then the movement of water across the descending limb. Okay, and that happens again and again and again until we get into the state of steady balance, or the steady state, and then that is how we establish the medullary osmotic gradient. So basically we have movement of solutes, so solutes are actively being pumped across the ascending limb of the loop of Henle first. This is the first part of that establishment. And no water is moving because this side of the loop of Henle is impermeable to water. Secondly to that, the descending limb now has a gradient, right? So because the interstitial fluid now has those solutes, so the solutes that were pumped across the ascending limb is now out in the interstitial fluid of the medulla. And so now water has a gradient to move. So down the descending limb, where we have only water permeability, water can now move until it becomes in equilibrium with the interstitial fluid, okay? So the basis of the establishment of this gradient is solutes move across the ascending limb first. That makes the medullary interstitial fluid salty, right, as those solids move first, and then water move as we now have a gradient of high water concentration and low water concentration because of the solids that are now existing in that medullary interstitial space. Okay. So the result of the counter current multiplier is that we start off with fluid in the tubule with an osmolarity of 300, but by the time we get to the end of the loop, right? So we start off with an osmolarity here at 300. By the time we get to the end of the loop of Henle, we now have an osmolarity that is less than the osmolarity of our plasma. And so that's exactly what we want. We want the osmolarity of the fluid to now be less than the osmolarity in our plasma, because that's going to be a gradient. That's the gradient that we want, so that water can move from the tubule, where that fluid is, into the blood, into the plasma, where we have a higher plasma osmolarity. And so this is facilitating the water reabsorption. So as we go down the descending limb, the osmolarity increases. So we're starting with an osmolarity of 300 of this filtrate. As we gradually go down, we're losing water here. And so as we lose water, what's left in this tubule starts to get more concentrated, right? More solids are left behind. And so the osmolarity here gradually increases. Now, as we go up the ascending limb, the opposite happens. The osmolarity begins to decrease. So we're left with water because only solutes are moving. So as those solutes move out of the tubule, the osmolarity of the filtrate, that's the fluid that's left in here, starts to get more watery, right? It's getting more watery as solutes are able to move, but water is unable to move, okay? So we go from an osmolarity of 300 all the way down to an osmolarity of 1200, which is really concentrated, really salty. And then we gradually drop the osmolarity all the way back to 100. And now we have a gradient. Now it's less than the osmolarity of our plasma at about 100 milliosmoles. So again, just to summarize here, the result of the countercurrent multiplier is so that the fluid in the distal part of the tubule has an osmolarity of 100, which is less than the fluid in the interstitial space of that cortical part of the kidney. Okay, so now we have that gradient, that medullary interstitial gradient. Okay, so the next few slides are a bit repetitive. They're going to kind of go through how that gradient is set up, how we get the this movement to be in a system of steady state. So we're going to walk through how we get that medullary osmotic gradient. So the first thing that happens is we have tubular fluid that moves into the first part of the loop, the descending limb of the loop of Henle. And as we can see here, when this first starts to happen, the osmolarity of the tubular fluid is the same as the osmolarity of our plasma. It's 300 all across. And at this osmolarity, we have no gradient, right? So we're going to have no water movement because we have no gradient. Now, the first thing that happens is the ascending limb of the loop of Henle is going to actively transport sodium, chloride, and potassium into the medullary interstitial fluid because this part of the loop is only permeable to these solutes. The second thing that happens is because we now have a medullary interstitial fluid that has more solute than the tubular fluid, we now have a gradient for water to move, but only the descending limb is permeable to water. So across the descending limb, water now moves until it's at equilibrium with the medullary interstitial fluid. And at that time, we're once again in an isoosmotic state. But as we can see here, the osmolarity is slightly higher on this side and lower on this side. Now, this happens again and again and again and again until this gradient is slowly established. So we push more fluid down into that descending limb, and the osmolarity of the fluid that is newly pushed in is going to be lower than the osmolarity of the fluid that's going to be at the deeper parts of the tubule, right? It's going to be 300 that's coming in fresh from the cortical area and 400 for the areas that are deeper in the medulla. And the same sequence of events takes place again. We actively pump sodium, chloride, potassium across the ascending limb, and then we passively move water across the descending limb until we again get to a state of equilibrium when we've moved enough water to be at homeostasis, to be at equilibrium or in an isoosmotic state once again. And when we get here again, we can see that the osmolarity of the fluid deep down in the medulla is higher than the osmolarity of the fluid up here. And this happens over and over and over as you push more water down into the descending limb until we get to a steady state where even though we're pushing more water in, we now have the maximum gradient where the deepest part of the medulla has an osmolarity of 1400 milliosmoles, and the cortical area at the end of the ascending limb has an osmolarity of 100, and now it's at a lower osmolarity than we began with in the cortical part of the tubule. Okay, and so now we have the gradient that we want, and the system is in steady state, and that is how we establish the medullary osmotic gradient. Okay. Okay. Now let's talk about the role of urea in establishing this gradient. So there's another important component to establishing the gradient, and that is urea. So urea is generated by the liver. It's actually the way that we eliminate excess nitrogen, which is a breakdown product from things like protein that we eat. It's extremely water soluble, but it requires the transporters located on different parts of the tubule. So transporter UTA is located on the collecting duct, and transporter UTB and UTC are located on the descending limb of the vasa recta, right? So I'm going to pause here a little bit and kind of explain the difference between the vasa recta and the loop of Henle, because students often get a little bit confused with the anatomy that's happening here. So the loop of Henle has a descending limb, so the proximal tubule, then it goes into the descending limb of the loop of Henle, and then it goes to the ascending limb and then to the distal tubule and collecting duct. But the blood vessels, so I talked earlier about the blood vessels that are intimately connected with the loop of Henle. It's called the vasa recta. And this is what facilitates the reabsorption of water and solutes here. So solutes and water move from the loop into the vasa recta, which are the blood vessels that are also wrapped around the loop. but the orientation of the loop of Henle is going to be the opposite than what it is for the tube, of the vasa recta is going to be the opposite of what it is for the tubule. So we can see here that the descending limb of the vasa recta is what comes in contact with the ascending limb of the loop of Henle, and the opposite is true. The ascending limb of the vasa recta is what comes in contact with the descending limb of the loop of Henle. Okay, so as I speak about the ascending and descending limbs, I'm going to be differentiating whether or not I'm speaking about the loop of Henle or the vasa recta, because they're going to be in opposite orientations to each other. So the transporter UTC and UTB are going to be found on the descending limb of the vasa recta, and this is where we have the ascending limb of the loop of Henle. And so the reabsorption of urea here is what facilitates the reabsorption of water that is following that urea. So urea is also an integral part of establishing the medullary osmotic gradient, okay? So here we can see those transporters. We've got UTA on the collecting duct. This is facilitating the movement of urea. And when urea moves, it's a gradient that allows water to move. So as urea is being reabsorbed across the collecting duct, water can also follow as well. It's going to be really important to reabsorbing water. And then here we see on the descending limb of the vasa recta, we have the other the other urea transporters that I was mentioning. So now let's speak more about the role of the vasa recta. So the vasa recta is, as I mentioned earlier, has an anatomical arrangement that is going in the opposite direction of the flow of fluid in the tubular structures. I'll say that again. The vasa recta has an anatomical arrangement that is going in an opposite direction to the flow of fluid that's happening in the tubule. So the flow of fluid that's happening in the tubule is going to be opposite to the flow of blood that's happening in the vasa recta. Okay, and the purpose of that is preventing the dissipating of the medullary osmotic gradient. That is preventing us from losing the gradient that we just spent so much time setting up, okay? Having the vasa recta facilitating the opposite movement of solute and water is what prevents us from losing the gradient that we just worked to set up with the ascending and descending limb of the loop of Henle. So in the descending limb of the vasa recta, which we can see here, here's the descending limb of the vasa recta. Remember, this is coming in contact with the ascending limb of the loop of Henle. So as water moves down the descending limb and water leaves the capillaries via osmosis, solutes can enter via diffusion. Remember, the solutes that are entering here are coming from the ascending limb of the loop of Henle, okay? Just remember that opposite configuration. And the opposite is true along the ascending limb of the vasa recta. So water moves into the plasma, and solutes are going to move out into the interstitial fluid. And so this is what is preventing us from losing our gradient. This is going to allow the osmolarity of the interstitial fluid to increase here again, which is preventing us from losing that gradient, okay? Also, the osmolarity here is going to be higher due to the lack of urea transporters. If you go back to this slide, remember I said that the descending limb of the vasa recta has these urea transporters, whereas the ascending limb does not. Okay, and that is going to allow for a higher osmolarity because there aren't any urea transporters here. And remember, where we have the urea transporters, salt is moving, urea is moving, and then water is following. So the osmolarity there would be lower, but because we don't have that happening here, the osmolarity here is going to be higher. All right. Okay, let me pause for a second and see if there are any questions. We're running out of time, so I'm just going to see if there are any questions before we kind of go ahead. Okay, so I don't see any questions. So to kind of wrap all of that up, we're going to speak here about um, the water movement along the distal part of the tubule. But I want you to have what we just talked about as a backdrop in your mind. So the whole purpose of everything we just talked about is so that the osmolarity of the fluid at the end of the loop of Henle is now less than the osmolarity of the interstitial fluid and the plasma. And so now at the distal parts of the tubule, we can really see the movement of water taking place because we now have a gradient set up. So let's talk about the different parts of the tubule and how water is reabsorbed differently. So the proximal tubule, we have 70% of the water being reabsorbed. This is unregulated. Throughout the distal part of the tubule, and this is inclusive of the descending limb of the loop of Henle. So that first part of the loop of Henle, although this is not regulated, this is inclusive of that distal tubule. We see 20% being reabsorbed here. And then the collecting duct, which is the final part of the tubule, we see another 10% of water being reabsorbed. And this is going to be under the influence of ADH. And so that's going to be regulated. So just to kind of wrap this up, summarize this in a way that makes sense. The proximal tubule, 70% not regulated. The distal part of the tubule, including the loop of Henle, 20%. But remember, the loop of Henle is not regulated. The distal part of the tubule is. And then the final part of the tubule, which is the collecting duct, is regulated, and that's about 10%. Okay. So the water reabsorption that we talked about is dependent upon the gradient that we established. So the medullary osmotic gradient, which is established by the countercurrent multiplier, and remember the countercurrent multiplier is just a fancy way of saying that the ascending limb moves solutes and the descending limb moves water, right? And that happens over and over and over again until we get this gradient. And that is dependent upon the different permeabilities, right? The fact that the ascending limb is not permeable to water and the descending limb is only permeable to water is what helps to set up that mechanism and helps to establish that gradient. Water permeability is also going to depend on the channels that are inserted into the distal parts of the tubule. So basically in the collecting duct and in the distal convoluted tubule, there are certain channels that are called aquaporins. And we talked about aquaporins and we kind of introduced it in one of our previous units. And it's basically a channel that facilitates the movement of water only. And so we have aquaporin 3 channels that are in the basolateral membrane always. And we have aquaporin 2 channels that can be inserted into the apical membrane only under the influence of ADH or antidiuretic hormone. So if we have lots of ADH in the blood, remember that's coming from the posterior pituitary, it's going to stimulate the cells of the distal tubule and the collecting duct to insert more of those aquaporin 2 channels to allow more water to be reabsorbed. But on the basolateral surface, we always have aquaporin 3 channels. They're not influenced by any hormone. Okay, so when the membrane of the late distal tubule is impermeable to water, water cannot leave the tubule because we don't have those aquaporin 2 channels on the apical membrane. So we cannot reabsorb water, and then more water is going to be lost in the urine. This is going to make the urine more watery or have a lower osmolarity. Whereas if we have ADH in the blood, if we have ADH being secreted from the pituitary, it's going to be a signal that we need to hold on to more water. So ADH is secreted from the brain during times of dehydration or during times of hemorrhage. ADH is also something that doctors give exogenously. So think about a patient who may be bleeding out or a patient who may be in shock or dehydrated. Your doctor is going to exogenously administer this ADH, and that is going to stimulate the insertion of aquaporin 2 channels into the apical membrane of these distal parts of the tubule, and that will allow more water to be reabsorbed from the tubule back into the blood so that you don't lose excess water during those states of shock or hemorrhage or dehydration. And so that is going to allow the urine to be concentrated to its maximum concentration, meaning it has very little water and a lot of solute, and that is about 1,400 milliosmoles. Okay, so the maximum amount of water we absorb depends on the length of the loop of Henle. And I kind of alluded to this earlier when I talked about animals like desert rats having really long loops of Henle. The longer the loop of Henle, the higher I can get my concentration of my urine, the higher I can get the osmolarity of urine. If I have a really short loop of Henle, then I won't be able to concentrate my urine, I won't be able to conserve or reabsorb more water. And so animals like camels and those rats that I talked about have a really long loop, so they can get the osmolarity of their urine to be even higher than 1,400 milliosmoles, and they can really conserve the maximum amount of water. So this table kind of, or this illustration, this schematic kind of shows the difference between urine that has a really high volume or really low osmolarity, meaning that urine that is really watery, and you want to kind of equate this to someone who is well hydrated or overhydrated, or maybe even someone who has a deficiency of ADH, because that's a thing too. If you're deficient in ADH, then you basically lose water excessively, and that can become pathogenic. So here we have urine that is mostly water. It has a very low osmolarity, so about 100. And remember, this is the osmolarity of the fluid at the end of the loop of Henle. So there was no water reabsorbed at all from the end of the loop of Henle to the point where it's being excreted, okay? On the other hand, let's say we have someone who's severely dehydrated, who is hemorrhaging or is in shock. They are going to absorb the maximum amount of water possible, okay, to conserve as much water as possible. And they may be under the influence of ADH secreted from the pituitary or ADH administered exogenously, but that is going to insert lots of those aquaporin 2 channels into the membrane and facilitate maximum reabsorption of water. And so at the end of the tubule, we're going to have a urine that is low in volume, that is really highly concentrated, and that has a very high osmolarity, okay? And so this is kind of why when you're drinking lots of water and you're well hydrated, your urine appears more clear and you probably have more urine more often. Whereas if you're not very well hydrated, if you're dehydrated, if you don't drink enough water, your urine is probably very, very yellow, very heavily pigmented, very concentrated, and probably a small amount of volume. Okay, bearing all of that in mind, we want to talk about the obligatory water loss. So this is the minimum amount of water that you must excrete per day. So even in states of dehydration, the minimum water that you must excrete is 440 milliliters. We kind of threw around that value a little bit earlier, but this is a better kind of application of how we get that 440 milliliters. So at a maximum osmolarity, your urine is 1,400 milliosmoles. At a minimum osmolarity, we saw that your urine is about 100 milliosmoles. So even during a state of absolute dehydration, in order to eliminate necessary toxins and waste products, you must eliminate at least 440 milliliters of water. That's called the obligatory loss. All right, so here's another set of checkpoint questions that I'm going to ask you guys to go over. So far that's 3 set of checkpoint questions. And we'll start off our session tomorrow with these 3 sets of questions. So I think we